Hi, my name is Jared Anderson,
And I'm Chris Duffy.
and we're going to be presenting the project that we completed for a video game called Snake, with some extra design patterns thrown on top of it to kind of update the concept of it. Um, what is Snake? Snake is actually not one particular game. It's actually a family of video games. It was developed in the mid 1970s. It was popularized in a game called Blockade, developed by a company called Gremlin. The general idea of it is that you have a player has a snake-like object which they maneuver around in a bounded canvas on a video screen. The basic idea of the game is to maneuver it around the screen and try to pick up different food type objects. There's a bit of variability across different platforms. Generally speaking, though, the idea is to maneuver the snake towards food, which allows the snake to grow in size. So each time the snake object eats a food object, then usually another length or partition is added to that snake, making the snake longer and longer the more food that it eats throughout the process. The in common applications, the idea is that the longer the snake becomes, the more difficult it is to maneuver around the screen. And if you maneuver the head of the snake back into the body, then the gameplay ends. Or if the head of the snake hits some sort of like enemy object or enemy sprite, gameplay at that point ends too. So it's actually a very simple and straightforward game. And the difficulty is just trying to maintain a semblance of control as the snake grows in length. And the idea here is not to kind of recreate the wheel, but kind of to put a new spin on it, to kind of update it via design patterns. So what are design patterns? Object-oriented programming can be very esoteric and can become quickly convoluted just due to the density of any given program that's implemented. The project that we pursued here in Snake quickly reached those heights, so we had to implement design patterns to kind of constrain it here. Design patterns are strategies to kind of templatize the code that would otherwise become very complex and unmaintainable very quickly. You know, for example, if someone was going to use object-oriented programming to design kind of like a class of ducks, what would be kind of the approach of designing this class? You know, a lot of people would use inheritance to create like different flying methods for different duck classes, different behaviors. You know, some ducks would quack, some wouldn't. Some ducks would fly, others wouldn't. And so this kind of complexity becomes problematic as programs progress. The first of the three patterns that we decided to use in this project was the strategy pattern. We thought that this would be kind of a good idea to throw in here. The strategy pattern itself is a behavioral design that selects an appropriate algorithm at a runtime, and so it gives the program a bit of kind of an air of flexibility as opposed to being hard-coded within the program. The algorithms themselves are encapsulated and interchangeable, and so that allows the client to select the appropriate algorithm given the context that it's in during the course of the program. So it's not just relegated to running one specific algorithm. It has a variety of choices that it could implement. The second one was the observer pattern. The idea behind observer pattern is to kind of have a subject object that maintains this list of observers. So the subject is responsible for being for keeping track of state within the program, and then it broadcasts any changes to that set of observers. So it's kind of, it's popularized in event-driven scenarios, and we thought that it would be appropriate for this particular project, given that it was a game design. And so there's a lot of event-driven processes that are present within the course of the game. It's kind of akin to how newspapers work. So instead of each citizen being responsible for kind of keeping track of the news themselves, they can rely on a newspaper to be notified of different changes and different information that becomes available. The final one that we utilized was the decorator pattern. basically the idea behind this is that you want to have behavior that can be added dynamically to an object without affecting the functionality of the other objects that are within the class. You want to extend the functionality of objects. You don't necessarily want to fundamentally alter them within the class, because that could have all sorts of unintended side effects. And so you want to be able to kind of tack it on. It's akin to, you know, adding a porch onto a house instead of having to, rebuild the house just to build the porch. And again, we want to adhere to the principle of modularity, so we can alter the runtime behavior instead of hard coding it. So those are kind of the design patterns that we had in mind. Some of the other initial considerations that we had were kind of were definitely different than what we ended up with, just because as we progressed within the course of programming the project, we realized that certain things would be easier, certain things would be easier to explain, and we wanted to kind of keep things flexible as well. Initially, we planned on doing the entire project in Java, allowing for the direct implementations of the patterns that were discussed in the class, and we also wanted to use a persistent database to store player and game information. We realized kind of in the course of designing the game that the dynamism of the game was kind of being constrained unnecessarily. So we decided to alter course and program this in a browser-based format using JavaScript and another JavaScript library called Pixie. And we ended up retooling quite a bit of the project, so we could not only create a richer project, but also to implement the patterns in novel ways, which we're going to be discussing here shortly. So those are that's kind of the initial considerations of the game. At this point, we're going to switch over to footage of actual gameplay. So we'll be doing that right now.
All right, so this is an actual clip of gameplay. Let me just roll the clip here. You can see that we ended up going with an online multiplayer version of Snake. This is written in Node.js, and it's using the Socket.io library so that we have an HTML, JavaScript, and CSS client side connecting to JavaScript server. And this is real-time multiplayer. All those little snakes you see running around are actual players. They're controlling the snake with their arrow keys.
Yeah, and as you can see here, we decided to go with the multiplayer paradigm just to kind of spruce things up to make it more interesting in terms of gameplay. But we also thought that it would be a good idea to implement this because in addition to other considerations, we thought it would be good for the design patterns that we wanted to implement in this game. As you can see here, there's a number of different objects that are present in the game as well. And we'll kind of discuss our thinking behind kind of using decorator patterns to get all of those established within the game as well. And yeah, as you can see here, the idea is that if the snake becomes too long, it kind of becomes a little unwieldy to navigate throughout the canvas.
Yeah, this was definitely a fun project. It's always fun to build a game, but also the using Socket.io and using Heroku to host an online testing server was a really smooth process, and we ended up with a product that works really fast and felt really good to. Oh, you just see me. I'm so devastated up there. I just died when I hit that skull. It was a really good product in the end. What's really cool about this is that the only things that we're handling on the client side are user input, as in what buttons are you pressing on your keyboard, and graphics. So displaying the actual sprites to the client. But all of the logic, where the snakes are, how long the snakes are, what items are appearing, what enemies are appearing, are all being handled on the server and then being passed over to the client. And so in that way, we can sort of abstract the game logic away from the render logic. And we used, like I said, we used Node.js for the server, and then we're using a library called Pixie.js, which makes use of WebGL the WebGL canvas on HTML5 to render all these sprites on the client. And that also, if you haven't ever tried it, great library and really fast.
Yeah, and it's also really interesting to note too, you can kind of see some of the ghosts here that are present within the game. We thought that it would be a good idea to have, you know, kind of different functionality to extend their ability to act differently depending on how, yeah, and then you can see I just died when I ran into a slime creature there. You know, we want to be able to extend the, in theory, we'll want to be able to extend their behavior to act in different contexts. So, you know, some of them will kind of spin if they have a certain method, or they have that method baked in, and then others will act differently depending on how they're randomly called through the course of the game.
Yeah, and one other, right now you're seeing Jared is that blue snake, and he's the only one playing at this point. And then somebody else just loaded in as I said that, to make me look like a fool. But you'll see in a second here, once Jared's snake dies, he's going to go back to a menu screen. And that menu screen is still going to have the real game playing in real time in the background. And also, it's got high scores that are saved on the server and pushed out to the client. And it's showing some information about who's playing right now. The names of, you can see my friend Sterling was playing as Solvency, and I'm also in the game as the Green Snake. So even on the menu screen, we're able to keep receiving those socket events and push that data out to the client, which was pretty fun to be able to do.
Mm-hmm.
Cool. So then now that you've got an idea of what the project was, let's zoom in and talk specifically about. Okay, so the first pattern, and really the main pattern that we used for this project, is the observer pattern. And everything about this game is event driven. So there's a couple of different places where we're using the observer pattern, but the really cool one is between the server and the client. So the server, we're importing a library called socket.io, and that allows us to make an instance of an IO object. And that IO object, it stands for input output, obviously. And it allows us to create new sockets every time a client connects to the server. So the IO object has an array of sockets, one for each connected client. And then we're able to add on specific string event names functions to each of those sockets. So when we create a new socket, we give it some specific functionality to the game and then hand it over to the client. We're also able to, as the game does stuff, emit a specific event names to the client with some piece of JSON data. So in this case, the game state. The most simple example of that would be that the server has an instance of the game, and game connects over to a very big custom class called game that it ended up being like 500 lines of JavaScript or something. But every tick of the server, the game loop runs its update method, and the game will return its current game state. That means the position of all the snakes, the position of all the enemies, the length of the tails, the position of all the items. And those are packaged into a single JavaScript object, which is then emitted from the IO object to the client socket. And so on the client, we have this socket that we've been handed from the server, and that socket is observing the main subject on the server, which is the IO. Every time the IO gets an updated game state, it emits it out to every single client. So every client is able to listen to one server object, and therefore the clients are able to have a synced up version of the game that they're seeing. Because remember, on the client, the graphics engine, which graphics is a custom connector for Pixie that we wrote. All that graphics is doing is displaying the last data set that it got from the server, but there's no logic happening on the client. The other event system that we have is observing the browser's key press events. So anytime you press a button on the keyboard, your browser, Chrome in this case, will emit a keyboard event. We are listening for those keyboard events in a custom class called input handler, and then we're handing those keyboard events to the client socket so that it can emit events like turn snake or start game. And then that passes from the client socket to the IO object, which can then pass it to the game and make the game logic happen. So that's a very brief overview of how we're using the observer pattern in this game.
Yeah, so the next pattern that we decided to implement was the decorator pattern, as opposed to the previous pattern, which mostly related to the functionality of the server. We use the decorator pattern to kind of wrangle all of the game objects that became available, that become available through the course of the game. The way that they're initialized is through random calls in JavaScript. So based on certain percentages, certain objects will become available on the canvas for viewing. So as you can see here, there's a banana class, apple class, a sword class, so on and so forth. Each of these objects in the constructor, they contain an item parent and then the string image. These relate back to the item. And that kind of goes back to the idea with the decorator that we want to make sure that we're not relying on inheritance explicitly to get the functionality that we want out of this. We want to make sure that the behavior that's added to the individual objects is done so dynamically without affecting the behavior of the other objects from the same class. So it's kind of all adhering to that single responsibility principle. So each of the in the constructors of each of these objects, you have the item parent, and that all relates back to that item interface up there. Each of the objects contains the X and Y position, as well as the string, the string image, and then a reference, an item parent reference going back to that interface up there as well. We talked about possibly adding further functionality to this, making sure, or having fruit that could possibly spin, or things like that. That kind of relates back to that idea. We weren't able to implement it due to other constraints, but it kind of goes back to that idea that you can have, or if you wanted to have like an apple in a banana in an orange or something like that. It's that idea that you can kind of recursively work through those objects to call each one and then return the object that you want back. So that really kind of adheres to that idea of decorating each object along the way, instead of having to kind of work through it explicitly, and it'll return it all in one fell swoop.
Yeah, that's a really good point, Jared. And like Jared was saying about how we could have wrapped a specific item, like we're already at every specific item is wrapped around an instance of the base item class. We could have wrapped specific items around specific items, as in continued to pass in multiple decorators for an item. But what we didn't have was good images that would let the players know what that meant. So if you were to wrap an apple around a skull, and then the apple would look like an apple, but also contain the functionality of killing the player when they ate it, that wouldn't be a very fun mechanic.
Yeah.
But that's pretty much everything about the decorator. Did you have anything else to say about that, Jared?
No, that was that's kind of the meat and potatoes of it right there. Again, as Chris noted, the idea that we'd want to maybe kind of wrap different objects in different objects would be a consideration going forward, but graphically it proved to be a little bit more arduous than we'd originally envisioned.
Yeah. So that gives you the idea of the decorator pattern, just wrapping that base item class in all these different specific classes. For the strategy pattern, we're using this for our mobs. Our mob class is the class for the enemies that either spin or move around the screen. So the idea here is that the main game has an array of mobs, and every time the game updates, every tick of the game loop, it's going to iterate through the mobs and call the update method on those mobs. Now, the mobs have different update functionality. So some of the mobs spin and some of the mobs move. We wanted to be able to polymorphically just call update on a mob, and the game doesn't need to know whether that's a moving mob or a spinning mob. It doesn't need to know what the update function does. It just needs to know this is a mob, and a mob has an update function. The update function will do something. It won't throw an error, right? So the way that we did this was by using the strategy pattern. We implement instances, or we build instances of either movable or spinnable, and then pass those into the constructor of mob as the update object. So a mob has an instance of an update object inside of it. Then in mob.update, what it's actually doing is calling update object.update. And that allows us to have sort of this polymorphic functionality where the game can call update on the mob and not know what that update is going to do, but know that it's going to have an update. And then the update object can be different. And this would be another place where there would be room for expansion. You could imagine a teleportable class or a flyable class or I don't know, shoot lasersable class, that perhaps those other things could happen on update. And as long as we built an update object that had an update function, we could plug it into this mob and it would work just fine with the game. We wouldn't have to change any of the game logic. We would only have to write a new update object class and then plug that in. So in that way, it's more extensible. Did you want to say anything else about design patterns, Jared, or you want to go back to some footage of the game?
I think this is a pretty good overview of what we wanted to accomplish in terms of implementing these patterns. Again, we originally envisioned a couple of different implementations, but we found through the course of development that these were the most natural fits for what we were looking to do. Really, we want to make sure that we were extending gameplay in a way that allowed us to have a lot of flexibility in object creation and object manipulation, and we were also able to implement some of that on the back end on the server as well. But yeah, I think
4 players right now. All right, 4 players right now.
This is fantastic. Yeah, this is the game that we wanted to design.
Hey, Orange Dude trying to kill the slime. The slime just moved through him. Did you see that? That's crazy. You can see pretty much how hype I am about this game actually working. This was a really fun project, and it was good to be able to incorporate all these design patterns so that if we were to come back to this and extend it, we would be able to build more functionality in the future.
Mm-hmm. Manipulate the objects further, like we talked about earlier in the presentation. But this is a lot of fun. It was challenging, but we're really happy with the final product here.
Yeah, and we're going to go ahead and within the link to the video, the link to this video in that text document that you already read, there's also going to be a link to the test server that we're going to leave up if you want to try playing the game, and a link to the GitHub if you want to grab a copy of the source code, and then you can extend it.
All right, fantastic. Well, I'm Jared Anderson.
And I'm Chris Duffy.
Thank you for watching.
Peace.